All right, hello everybody. Welcome back to Math Background for Machine Learning. So last time around we were talking about uh, matrices, linear operators in vector spaces. So the typical example of a linear operator is a matrix in Rn. And so today we're going to be talking about how to do computational work with matrices. So in particular, we're going to be talking about how to solve systems of linear equations. So if you remember, right, so the linear operator is an abstract idea. It's a function that takes one vector space to another. If we want to work with a linear operator computationally, we have to pick a basis for the input vector space and a basis for the output vector space. And then using those bases, we can get a coordinate representation of our linear operator, which is a matrix. And matrix multiplication is the same as applying the linear operator as a function. And if you remember as well, we talked about different patterns that matrices could follow. For example, upper or lower triangular or diagonal, or just plain sparse with no other pattern. And the point of these patterns was that we promised that some computational operations were going to be easier given those patterns. And so today we're going to talk a bit more about what kinds of computational operations those are. So the most common way to work with a matrix is to work with one of its factorizations. So a factorization is just if we have a matrix A and we represent it as a product of two simpler matrices B and C, or perhaps of three simpler matrices B, C, and D. So these factorizations are helpful if we can have the matrices B and C have one of the patterns that we talked about or some other convenient property. And as I mentioned, of course, the structure of a matrix, the coordinates in the matrix are going to depend on the bases we pick. And so we'll just implicitly fix a basis whenever we talk about these matrices. But remember, of course, that choosing a good basis can make a big difference. All right, so we've met one factorization already, the singular value decomposition, and that and the LU decomposition are maybe the two most common factorizations to use computationally. So let's go over those. I should say, if you want to compute one of these factorizations, there are algorithms for doing it. For example, you can compute an LU decomposition by Gaussian elimination. However, rather than doing it by hand for anything bigger than 3 by 3 or a 4 by 4 matrix, it's a much better idea to have your computer do it for you. So there are functions that do it in MATLAB, there are functions that do it in NumPy, and a ton of other tools that will do it as well. So I'm just going to describe the form of the factorizations and not how to compute them, because how to compute them is tell your computer to do it for you. All right, so in LU decomposition, we represent a matrix A as a product of two matrices L and U, where L is lower triangular and U is upper triangular. And so I should point out A here, we're assuming it's a square matrix, and its factors are also square, so everything is n by n here. You can use these factorizations to deal with non-square matrices. Conceptually, all you have to do is pad the matrix with 0 rows or 0 columns in order to make it square. Of course, computationally, you have to think about how to avoid explicitly iterating over those columns full of zeros. But for now, let's just assume everything's square. So A equals LU is the LU decomposition. And then the singular value decomposition, or SVD, we have A equals USV transpose, where U is orthonormal, S is diagonal, and V is orthonormal. Oh, and S also has to have non-negative diagonal elements. All right, so we've placed two very different kinds of constraints on the factors, right? Lower versus upper triangular, or orthonormal and diagonal. Both of these factorizations always exist, so you can always find them, and they are convenient to work with. We'll see how in a little bit. Let's see, and so if A satisfies some patterns, then there are special cases of these factorizations that are even nicer to work with. So if A is symmetric, then the LU factorization can be simplified to LD L transpose. In other words, we can say that U is equal to a diagonal matrix times L transpose. And if, in addition, A is positive semi-definite, the diagonal matrix is unnecessary, so it's just L times L transpose. This here is called a Cholesky factorization, where we do an LU factorization of a symmetric positive semi-definite matrix that's of the form L times L transpose. All right, the SVD can also be simplified when A is symmetric. So we can, so the general SVD has U and V be completely unrelated orthonormal matrices. But if we take a symmetric A, then we can have V be U times a diagonal matrix of signs. So the factorization looks like this: U S sigma U transpose. And if, in addition, A is positive semi-definite, then we can skip the matrix of signs and have S be just be US U transpose, so that we have just a matrix of positive diagonal elements, and U and V are the same matrix. And this, by the way, is the version that we saw before, US U transpose. So variance matrices are always symmetric because multiplication of scalars is commutative. And they are always positive semi-definite. That's maybe less obvious, but it's a few line proof. And so because it's symmetric PSD, we use the US U transpose version of a singular value decomposition. All right, so those are probably the two most common factorizations, and they're useful for a bunch of tasks. Maybe the most common single task is solving sets of linear equations, which we'll get to in a sec. But here's an interesting example. You can use them to test whether a symmetric matrix is positive definite, positive semi-definite, or something else, which is to say indefinite. Or negative definite, I guess. Anyway, the point is you can test the positive semi-definiteness of a matrix. So if you take, for example, the LU factorization of our symmetric matrix A, the matrix A is positive definite if and only if the diagonal elements of D are strictly positive, and it's PSD, positive semi-definite, if they are non-negative. Similarly, if we take the singular value decomposition, A equals US sigma U transpose, the matrix is positive definite if and only if the diagonal elements of this product of diagonal matrices are strictly positive, and it's PSD if they're non-negative. So if you computationally want to test for PSD-ness, actually probably the fastest way is to try and compute the LDL transpose factorization. But it's slightly more numerically stable to compute the singular value decomposition and use that to test. All right. So now solving linear equations. So I want to first say how not to solve linear equations. This is a mistake that a lot of people make when they're beginning with numerical linear algebra. So it's very tempting to say, well, if we have a set of linear equations, ax equals b, we just multiply both sides by the inverse of a and say, well, x equals a inverse times b. And mathematically, that's true, but computationally, it's a very bad idea. So there are two problems with doing it this way. So the first problem is a problem of speed. suppose that A has a nice pattern. Let's say it's sparse. Well, there's no reason that A inverse will have a nice pattern. And so you could go from a sparse matrix to a dense matrix when you compute the inverse. And if you have, let's say, a million by million matrix with 10 million non-zeros, you can work with that perfectly fine in a computer. But a dense million by million matrix is going to grind your computer to a halt while it's swapping memory out to disk, or possibly just cause it to segfault. And so, computationally making the inverse is a bad idea there. Maybe more subtly, there's a problem with round-off error. So even if it's possible to solve this equation to a high degree of accuracy, in other words, to find an x such that ax equals b to close to machine precision, if we compute A inverse b, we won't necessarily get that x. And so just to put some numbers to this, a double precision floating point number has a relative error of about 10 to the minus 15. And if we do, a few computations, maybe a typical error would be 10 to the minus 12. But if we try and compute A times A inverse B, and that's supposed to be equal to B, but if we do it computationally, we're going to be off by a lot more than 10 to the minus 12. We could be off by 10 to the minus 3 very easily, or even 10 to the plus 3, right? So in other words, you can get so that the round-off error completely swamps the actual answer if you try and solve linear equations by inverting a matrix. And so there are valid reasons to try and solve Ax equals b by computing A inverse, but most of the time, unless you are sure that that's the right thing to do, you shouldn't do it. All right, so how should you if you don't want to compute an inverse? So the way we'll do it is with matrix factorizations. And so let's see. So if we have, for example, an LU factorization of A equals LU, we can multiply first by L inverse and then by U inverse and get X equals U inverse L inverse B. And so it's typically, or at least in many cases, computationally efficient and numerically well-conditioned, in other words, not subject to very much round-off error, to find L and U, to find this factorization. We still don't compute L inverse or U inverse explicitly, but it turns out that there is a fast algorithm for solving an equation with an upper triangular or lower triangular matrix. It's called back substitution. So we can solve Ly equals b, right? So that's equivalent to saying y equals b times L inverse, but this is going to be numerically better conditioned. And then instead of multiplying by U inverse, we solve Ux equals y, right? And so just to say that again faster, if we want to solve the equation Ax equals b, and if we have an LU factorization for A, what we do is we solve two triangular systems of equations, one after the other. We first solve Ly equals b to get y, and then we solve Ux equals y to get x. And in contrast, so there we have never formed a matrix inverse, right? The only things that we've done are find a factorization of a matrix and do back substitution. And both of those are computationally efficient and numerically well-conditioned. Another nice property is that if we have Ax equals b1, or Ax1 equals b1, Ax2 equals b2, right? A bunch of equations with the same matrix but different right-hand side vectors. We can compute the factorization once, and since the factorization is typically the most expensive step, it really saves a lot of time to reuse it to solve each one of these equations. So if you're using MATLAB, you're actually, when you use the backslash operator for solving systems of linear equations, you're automatically using LU decomposition, at least as long as A is a general matrix. MATLAB is actually maybe a little too clever, but what it does is when you invoke the backslash operator, it tries to look at this pattern of non-zeros in A and choose an appropriate algorithm for solving that particular system. And so, for example, if A were already triangular, then MATLAB would automatically do back substitution instead of trying something more expensive. Or if A is a general pattern, it first tries to LU decompose A and then use back substitution. All right, so that's with an LU factorization. You can also solve linear equations using the SVD. So if we factored A equals USV transpose, then if you remember, the inverse of an orthonormal matrix is its transpose. And so we can efficiently and stably invert an orthonormal matrix. And then the inverse of a diagonal matrix, we just take 1 over each one of the diagonal elements. And so if AX equals B and A is USV transpose, then X is V S inverse U transpose B. This is slower, typically. The amount by which it's slower depends on the structure of A. For a general A, it would be, only a small factor, like 3 or 4 slower. If A had a sparsity pattern, then there's no reason that U or V would be sparse, and so this could be arbitrarily more expensive if you started with a sparse A. And the only place where we can get numerical problems is if the diagonal elements of S are small, because multiplying by an orthonormal matrix is possibly the most well-conditioned operation that we can do. And so the only way we're going to get round-off error is if the diagonal elements of S have a very wide range. So maybe one of them is 1,000,000 and another one is 10 to the minus 9. And what people will do is they'll actually, to avoid this round-off error, they will zero out the small entries of S. Or rather ignore the corresponding rows and columns of U and V. All right, so that's sort of the primer on solving linear equations. All right. So then the next question is least squares. So if A is not invertible, we might still want to try to approximately solve AX equals B. If we set X equals A pseudo-inverse times B, then one of two things will happen. If we're lucky and B is in the column span of A, then we'll actually get a solution, AX equals B. And if not, in other words, if there's no way to get AX equals B, what we'll do is we'll get something that minimizes the norm of the residual vector, the difference between AX and B. So this is sometimes called a least squares solution because it minimizes the norm squared of AX minus B, which is the sum of squared elements of the residual vector. And so if we want to do that computationally, the SVD is a great way to do it. We'll form the singular value decomposition, USV transpose. U and V are invertible because they're orthonormal, but one or more diagonal elements of S will be 0, and so S won't be invertible. And so to find the pseudo-inverse of A, all we need to do then is find the pseudo-inverse of the diagonal matrix S, and that's actually really easy to compute. We take SII inverse on the diagonal wherever SII is not 0, and we just take 1 over 0 to be 0, which we can't usually do, but for the pseudo-inverse, that's what the algorithm is. And so then once we have the pseudo-inverse of S, the pseudo-inverse of A is V S pseudo-inverse U transpose. And then here, this says again what I mentioned before. If our matrix A was close to singular, some of the diagonal elements of S will be close to 0. And so what we can do is pretend that those elements are exactly 0 and take the pseudo-inverse. Okay, so there's a question on Piazza that just asks to explain the singular value decomposition again. And so here, let me start again by going over the definition. So the definition, we have a matrix A, and we want a matrix factorization. In other words, we want to write A as the product of several matrices that have nice properties so that it's easier to work with them. And so there are a ton of different matrix factorizations depending on the properties that we ask for in the factors. But here in particular, if we write A equals USV transpose, where we have the following properties, U has to be orthonormal, S has to be diagonal with non-negative diagonal elements, and V has to be orthonormal, right? So that's the definition of a singular value decomposition. I guess the first thing to say is that beyond that definition, you don't actually need any intuition beyond that. You just need to know that you can always find a singular value decomposition, meaning that given any A, you can call some code in SciPy that will give you U, S, and V, that when you multiply them back together like this, you'll get A. So you can use it without having any further intuition for it. And in particular, you can use it to find the pseudo-inverse the way I described in the section 4 here, right? As far as intuition goes, so an orthonormal matrix, right, what it can do, it can rotate and it can reflect, right? So you can, basically to make an orthonormal matrix, basically what you can do is you can concatenate a sequence of transformations where you pick a couple of coordinates and rotate by some defined angle along those coordinates, or pick a coordinate and flip it, or actually pick a direction and flip along that direction. And so if you concatenate any sequence of those operations, you'll get an orthonormal matrix, and you can get any orthonormal matrix that way. And so what this is saying is that you can take a general linear transformation and you can write it as write it in the following form, right? First, we do an orthonormal transformation, that's V transpose, and so we do some rotations and flips, and then we scale on the coordinate axes. So we stretch or squash the vertically, horizontally, right, like along the coordinate axes. And then we do another orthonormal transformation. So it's not at all obvious that that should be true. It's a deep theorem that somebody proved about linear algebra, that you can represent any linear transformation this way. But it's kind of, it's kind of an interesting and useful fact. In terms of symmetric matrices, it's maybe a little bit easier to understand the singular value decomposition, right? So here, this is the SVD of a symmetric matrix. So it's an orthonormal matrix and the inverse of that same orthonormal matrix, and then a diagonal matrix with positive or negative elements. And so what we're saying here is that for a symmetric matrix, we can always represent it as do some set of rotations and flips, scale or flip the coordinate axes, and then rotate back, right? So what that's saying is that, another way of saying is that if you choose the right basis, then any linear operator can be made diagonal, right? So that it only stretches or squishes independently on all of the coordinate axes. So I hope that's maybe a helpful set of intuitions about SVD. There's another question about how you can how you can understand that the factorizations correctly solve the linear equations. I guess, I mean, in order to show that they're correct, right, it is like it's fairly simple to show that they're correct, right? So if you have A equals LU and you want to solve AX equals B, right? So that's LUX equals B, right? So if we write y equals ux, right, then it has to be the case that ly equals b, and so we can, if we can solve this, we get y, right? And then we then know that ux equals y, so solve this for y, and then we know ux equals y and can solve this for x, right? So it's fairly straightforward, at least from a symbol pushing an algebra manipulation point of view, to show that it is correct to solve a system of linear equations that way. And you can write essentially the same thing for a singular value decomposition, except that there's 3 steps. You first have to solve V transpose and then S and then U in order to get the SVD, to use the SVD to solve some equations. In terms of worked examples, let's see. So it's really easy to generate worked examples using MATLAB or SciPy, because you can just take a 2x2 matrix and or a 3x3 matrix, compute its factorizations, and do these manipulations one after the other. I don't think that I can generate an example on the fly, but maybe we can post an example to Piazza after class if people would find that helpful. So let's plan to do it that way. Another suggestion, actually, I think that there are, I think, Wikipedia pages on the appropriate factorizations will have examples. So so if we look, I'm looking right now at the Wikipedia page on Gaussian elimination, which for some reason I'm not able to load right now. All right, well, so for worked examples, I think the best thing is going to be we'll post a worked example or two to Piazza after class. All right, so let's see, we were just at least squares solution. I think we finished that, so let's go to these notions of subspaces. Oh yes, so specifically people are interested in stability of computation. So I'll definitely make sure that we post examples that show that. All right. Yes, subspace, span, orthogonal complement. So if we have a set of vectors, x1 through xk in a vector space, the set of linear combinations of those vectors is a subset of V. And it's also itself a vector space. It's pretty easy to show that. So in order for it to be a vector space, right, it just means that it's closed under addition and scalar multiplication. And it's pretty clear that it is, because if we add together, something of this form, right, a1x1 plus up to akxk with b1x1 up to bkxk, we'll just get a1 plus b1x1 up through ak plus bkxk, right? So we'll be able to represent the product as a linear combination of those vectors. Same thing with scalar multiplication. The scalar multiples just go through and multiply the AIs. All right, so the span of this set of vectors is itself a vector space, and therefore, since it's a subset of the original vector space and is itself a vector space, it's called a subspace. And if the vectors are linearly independent, they form a basis for this span. So suppose that this span S is a strict subspace of V, meaning there are vectors in V that are not in S. Then we can take one of those vectors and add it to our set of vectors, and that's going to make a larger subspace, right? And then if there's still something missing, we pick an arbitrary one and add it to our set, right? And the subspace gets bigger until finally, as long as the space is finite dimensional, we'll eventually get a basis for all of V. If we're in an inner product space, we can always choose these additional vectors to be orthogonal to all of the vectors in X. All right, and so we'll call these new vectors Y, and the span of Y is going to be called the orthogonal complement of S, the original subspace, and it's written as S with a little perpendicular sign, superscript. If we take the orthogonal complement twice, that gives us back the original subspace. At least it does in a finite dimensional examples. And then if we take the sum of S and the orthogonal complement of S, right? That's just the sum in the sense of a set sum, x plus y for x in S and y in S complement. Then the sum of S and S complement is going to be the entire vector space V. Useful special case is that the span of an empty set of vectors is just equal to the set containing the origin, and the orthogonal complement of the entire vector space is defined to be just the set containing the origin. These are useful in understanding the action of matrices in the following way. So let's take an m by n matrix where m is bigger than n, or at least as large as n. We can write span of A. So before we wrote span of a set, and now we're writing span of a matrix. And that's just the column span, right? So we take our set to be the columns of A. And so the vector A times X, right? It's a linear combination of the columns of A where the coefficients are equal to the components of X. And so AX is in the span of A. And so another name for the span is the range of the matrix A. The null space of a matrix A is the set of vectors X such that AX is equal to 0. That's also called the kernel of A. And there's a famous theorem of linear algebra that says that if we take the span of A and the null space of A transpose, then those are orthogonal complements of each other. So that means that every vector in the range of A is orthogonal to every vector in the null space of A transpose, and together all of those vectors sum up to form the entire vector space. And we can define the range or the span and the null space of a linear operator the same way. The range of A and the null space of the adjoint of A are orthogonal and sum to all of V. All right, so that's how to computationally solve linear equations. This is useful to know because there are a lot of algorithms that, in the end, a major step of the algorithm boils down to solving a system of linear equations, and so it's good to know how to do that well. And as a matter of fact, we're going to see shortly some algorithms where basically solving the set of linear equations is essentially the entire algorithm. We just have to pick the right set to solve. So I think that's a good place to pause for a second. And I'm going to release a quiz now. So, all right, so the quiz is now released on Canvas. I'll post a link on Piazza shortly. The quiz is covering two things. It's got a little bit of stuff on linear algebra still, just to make sure that nobody forgets linear algebra. But it's also checking scalar ability to do scalar derivatives. And so we're going to assume, we'll review it briefly, but we're going to assume that everybody comes in with the ability to take scalar derivatives. But just to check that assumption, I've gone ahead and published the quiz. If you like, if you need a little bit of a reminder, the syllabus shows the next thing on the syllabus is matrix differentials, and it starts with the first three sections are a reminder about scalar derivatives. All right, so we'll pause for a second and we'll come back after everyone's had a chance to work on the quiz. All right. It seems like most people did do pretty well. We're going to obviously leave the quiz open until half an hour after the end of class, like we usually do. Um, but let's get started back on the rest of the lecture notes today. So we are done for now with linear algebra, or not done. We're going to continue to use it, but we're not going to have lecture notes specifically about it. And we're going to go now to calculus that has matrices for the variables or for the outputs of functions. Um, and so this is, my assumption is that everybody's going to be fairly familiar with taking scalar derivatives, but I suspect that this view of matrix calculus will be not as familiar for most of you. The reason that we're talking about it is that there's a lot of instances where it helps to be able to rapidly take the derivative of expressions that involve matrices, either as inputs or outputs or intermediate quantities. And you can do that with just a knowledge of scalar derivatives, right? Like you can write out all of the matrix multiplications in terms of, explicit sums and keep track of, 57 different indices on each one of your expressions. And the reason, so you can do that, but it's slow and it's error prone compared to treating the expressions just as matrices. And we'll see some examples of that later. But that's the point of doing it this way, right? So I'm going to give you a summary of how to work with derivatives of matrix expressions. And these rules are going to be sort of much faster to apply once you're familiar with them. All right, so let's start by briefly reviewing scalar derivatives. So if we have a function f with a real input and a real output, we write f prime for its derivative with respect to its argument. If the argument is called f, we can write df dx or d by dx of f, right? We can write f double prime for a second derivative, f triple prime for higher derivatives. If a function depends on more than one variable, so let's say it depends on both x and y, we can write partial with respect to x of f or partial with respect to y of f. And what that's doing is talking about the derivative with respect to x or y holding the other one constant. So that's called a partial derivative. When we get to matrix valued expressions, it becomes sort of the number of permutations of this becomes rather large, and so it's good to keep firmly in your head which variables are supposed to be being treated as which expressions, which symbols refer to constants, and which symbols refer to things that we're varying. It's also helpful to have a notation for evaluation. So we write a vertical bar with a subscript x hat to say that we're evaluating a function at a particular value. That notation is useful, again, to help make explicit the distinction between things that are variable and things that are constant. So we have to keep something variable while we're taking a derivative with respect to it, but then later we might evaluate it at a constant, and then it becomes constant for the rest of the calculation. And then a notation that you might be very familiar with if you have an engineering background, people will put a dot above a function to talk about its time derivative, right? So f dot is the derivative with respect to time, and f double dot is the second derivative with respect to time. And so what that means is we have a system where there's one scalar variable time, and there's a bunch of other variables that depend on time, and we're thinking of, f of x, y, z to be a function that varies in time because x, y, and z are varying in time. And so to talk about time derivatives specifically, we use the dots. All right. When we work with scalar derivatives, we're going to use the chain rule and the product rule and linearity of differentiation. So if A is a scalar, f is a function, b is a scalar, g is a function, then the derivative of af plus bg is a times the derivative of f plus b times the derivative of g. That's linearity. And then the chain rule and the product rule. Right, so this is the form that I first learned, that the derivative of f of g of x is f prime of g of x times g prime of x, or the product rule f times g prime plus f prime times g. And then, of course, you need to know the derivatives of common functions like constants, monomials, polynomials, trig functions, and exponentials and logs, right? So we'll assume that you remember those or can look them up. But that's the sum total of the scalar review, and that's mostly just to fix notation so that we're all working in a common notation. All right, so now let's start getting into higher dimensional objects. And the simplest higher dimensional object is a vector. Sorry, there's a question for review material for linear algebra on Piazza. The best review is Horn and Johnson, probably. Especially they have a chapter 0 of Horn and Johnson. And so the citation, the full citation for that is on Piazza. But it's a really nice textbook and reference for linear algebra. It's nice because it's pretty comprehensive and yet not that long. And so you can rapidly review things without having to go through, hours and hours of reading to find the concepts you need to review. So I recommend Horn and Johnson. All right. So derivatives that involve vectors. So there's two cases for where vectors could arise. They could be the input of a function or the output of a function. So let's talk about first the output of a function. So f of x goes from r to rn, and so we can write it by its component functions f1 through fm of x. And then we can collect all of these partial derivatives right into a column vector, the same shape as f of x, and that is that's what we mean by the derivative of a vector valued function. So graphically, we can think of a vector valued function as representing a curve, right? So here's an example. The blue line is a curve, and the derivative represents the tangent vector to this curve. Basically, it's the instantaneous velocity of a point that's moving along the curve as we change x at a constant rate. And so the length of the tangent vector tells us the speed, and the direction tells us, well, the direction that the point is moving. And so here's what that looks like, right? Here's the point that we're currently at. The tangent vector is this red whisker, and you can see that, if we were moving a point along the blue curve and we let it go at this point, this is the direction it would continue to move. All right, so the other way we can have a vector is as the input to a function. So this is a function from Rn to R. And so we collect all of the arguments into a column vector with components x1 through xn. And we write the, we say that the derivative is the row vector of partial derivatives. And so here we can think of it as representing a surface in Rn plus 1. So the argument varies across Rn while f of x determines the height. So here's an example just of a parabola in R2. And so there's a derivative vector here in red, and what this is telling us is the instantaneous direction of steepest increase of the function. And so that's called the gradient. All right, so you may have seen the chain rule for vectors in a previous calculus class, but it's actually, the nice thing about the way we've set up the notation so far is that it looks exactly like the chain rule for scalar scalar to scalar functions, right? So if we have f which takes multiple arguments and g that returns a vector of values, then we can take f of g, right, and take the derivative of that, f of g of x. And so df dx will then be df dg times dg dx. And here df dg is a row vector and dg dx is a column vector. And so when we multiply them, that means they're dot product. And if we write it out, it looks like this, right? It's the sum over all of these components of the product of partial derivatives along each one of those components. And so that's called the total derivative, right? It's the sum of products of partial derivatives. All right. So a good way to think about derivatives is with Taylor series. So if we have a function f and a point x hat and y hat with y hat equal f of x hat, then we can approximate f around x hat with the first order Taylor series, which is a linear function. So y is approximately equal to y hat plus a times x minus x hat, right? And so here we're saying that x and x hat are in Rn, y and y hat are in Rm, and A is a matrix in Rm by n, right? And so this generalizes the previous two cases where you have vector inputs and vector outputs, because we can always take either m or n equal to 1. And the matrix A in this case is called the Jacobian, or the first derivative. So we can write it out like this. The components of A, Aij, is the partial derivative of yi with respect to xj evaluated at x hat. And so just to warn you, there are some books that use the opposite convention from what we just described. Some take the Jacobian to be the transpose of the matrix that we just gave. Just watch out for the differences. Unfortunately, there's not a uniform standard. So if we look at a curve, the Taylor series represents a line that's tangent to the curve. And A is going to wind up being the matrix of partial derivatives. Same thing for a surface. The Taylor series represents a plane or hyperplane that's tangent to the surface. And the Jacobian matrix is again the set of gradients, and the components will be the slopes of the plane. So it'll tell you again the direction of steepest increase. All right, so so now we've reviewed scalar derivatives, and we've reviewed sort of common ways of dealing with multidimensional objects in derivatives. And now we're going to go to some notation that's going to help us generalize even further. And that notation is called differentials. So we're going to take the same Taylor series, right? So just to remind you, right, here's the Taylor series. Y minus y hat is equal to a times x minus x hat, right? And so we're just going to write that as dy equals a times dx. And so dy, you can think of it as being short for y minus y hat, and dx as being short for x minus x hat. And they're called differentials, right? We're thinking of them as a change in y and a change in x. So the expression here is just that the change in y is a times the change in x. Now, just as a notation thing, we changed the approximately equals in the Taylor series to an exact equality. That's a convention that's justified by the idea that we're thinking of infinitesimal changes. But this is actually, like, you know, the differential, you can think of it as being either infinitesimal changes or just a representation for Taylor series. So we don't have to work with infinitesimal y minus y hat. All right, so this is just a more compact notation for a Taylor series. It's, you know, exactly the same thing that we saw written in the previous section. But one nice thing about it is that it's suggestive now derivatives, because if we quote divide through by dx, we get dy dx equals a, which is saying that a is the first derivative of y with respect to x. Now, of course, we can't really divide by dx because division by a vector or a matrix is not directly defined, but that at least sort of gives a connection between the familiar notation for derivatives, where we have just an operator dy by dx or d by dx, and here where we've separated out dy and dx and we've given each one of them an individual meaning. All right, and so we're now we're going to now talk about how to manipulate, how to think about and how to manipulate this sort of Taylor series notation, dy equals a dx, which is called differential notation. We're going to talk about how to manipulate this notation to be able to take derivatives, and it's going to turn out that there are some derivatives that are easy to take this way that would be essentially impossible to take, or much more difficult to take. Not impossible, but just a heck of a lot much more pain if we tried to do it with ordinary scalar derivatives. All right, so when we have a Taylor series, right, the change in y is equal to a times the change in x, the matrix A, the Jacobian matrix, depends on x hat, right? And so it makes sense to be more precise and say a of x hat, right? And so the same thing in an expression where the Jacobian is not constant, we'll write dy equals a of x dx. And so here, right, in the Taylor series, we had a separate x and x hat. In the differential notation, we don't need that, right? There's only x and dx, and so we can think of x being the point where we evaluate it, so it's like x hat, and dx being like x minus x hat in the Taylor series. All right. So just another small bit of notation is that before we had a distinction between partial derivatives and total derivatives. Now, if there's many different variables, there's so many different conventions that it's not like we can take derivative while holding any subset fixed and varying any other subset. And so what we're going to do, our convention is to say that any variable that appears in a differential is one that we're thinking of varying, and any variable that doesn't is one that we're thinking of as holding constant. And so this is actually a nicer convention than the partial derivative one, because it says explicitly which variables we're considering as variables and which ones we're holding constant for now. And so there's an example here, right? If we have dl is equal to some function times dx plus another function times dy, right? So w here is constant because it doesn't appear in a differential, and x and y are potentially changing. And then we could make the example even more complicated by saying that x and y are functions of another variable t, so that dt is relevant as well. We can, again, quote, divide through by dt and get dl dt is equal to this expression here, which is in fact the correct expression for the total derivative of L with respect to t while we're holding w constant, right? And so, again, this expression, we don't have to say what we're holding constant. In order to say that this is the correct total derivative, we have to explicitly list out which variables are variables and which ones are being held constant. All right, so an example of how to use this new notation. So we're going to first go through this example using ordinary scalar derivatives, and then we'll show how to write it again in differential notation. So suppose that we have y equals f of x is equal to this squared norm of a residual, right? ax minus b norm squared over 2 just for convenience. So here, x and b are vectors, and a is a matrix, and y is a scalar. And let's say that we want to take the derivative. So why would we want to take the derivative? Well, maybe we want to minimize this residual error, right? So we can do that by taking the derivative and setting it to 0. But let's not worry about that. Let's just worry about taking the derivative. So I've written out here the way to do the scalar derivative of y with respect to x, right? So I just wrote out all of the matrix multiplications as sums, took partial derivatives with respect to each component of x, and then once we see this, we can compute the total derivative by recognizing matrix multiplications in this in that expression, right? So it's kind of fiddly. It takes a lot of ink, so to speak, and you have to be very careful about your indices in order to get it right. So instead of this, we can write the whole thing in our new notation as dy is equal to ax minus b transpose times a dx. Okay, and so this notation is, well, it's about equally compact as this, but it's much simpler than the intermediate steps. And so what we're going to do in a future set of notes is figure out how to derive that expression directly without ever having to go through this junk. All right. So I think we have time to oh, so somebody's asking on Piazza about the difference between total and partial derivatives. So let's see. So a total derivative means that, like if you take the, let's go back up to an example here, right? So this example here, right? So in that example, we have let's say f of g of x, where x is real and g of x is a vector, right? So and we'll just write f for the output of that, right? And so if we want the total derivative, df by dx, that's called the total, right? If we want that, then what that means is, oh, so sorry, one more bit of notation. We'll just say u is equal to g of x, right? And so the total derivative of f with respect to x means that we're considering all of the variables u and how they vary while we're computing this derivative, right? As opposed to, we could ask for the partial derivative of f with respect to u3, right? Which is just saying, forget about how all of the other variables are related to one another. How does, if we, imagine that they're all fixed and vary just u3, how does f change, right? So total and partial derivatives are basically saying something about what variables, how many interactions among variables we're considering. And I don't actually like the total and partial derivative notation very much. I actually think that the more flexible notation that we gave here, right, where we're just considering varying the variables that appear inside differentials, makes it easier to understand what's going on. All right. So let's see, we already did linear equations. So now I think we're not going to be able to finish this set of notes, but we might as well at least get started. And so there's the next couple of sets of notes are about tools for working with derivatives in this new differential notation. And just like always when we're working with derivatives, there's sort of three main tools: linearity, the sum rule, and the product rule. The chain rule and the product rule. The sum rule as well, but that's much easier to work with. That's an example of linearity. So linearity, the chain rule, and the product rule. And we'll get into those later in this set of notes. But before we do that, what I want to point out is that, again, we're in a situation where we're working with a lot of different vector spaces potentially. And so in order to keep from getting confused, it's a good idea to type check your expressions. So what that means is just, make sure that you know the types of all of the variables, all the functions, all the intermediate quantities. And that sort of can help A, avoid errors, and B, understand what's going on when you're evaluating the expression. And so we'll have an equation that looks like, f equals something that involves the variable x. And so that describes how a variable f in some vector space V depends on another variable x, which is in some vector space U, right? And so this right-hand side of the equation is going to represent the function that tells us how to take an argument that's in the vector space U and compute a value that's in the vector space V, all right? So if we have an expression like this and we take the differential, it's going to look like df is equal to some expression that involves x and dx, right? And so x is going to be in U, dx is going to be the same vector space as x, so it'll be in U as well. And then df will be in the same vector space as f, namely v. And so this right-hand side here represents a function where you take two arguments in U, namely x and dx, and compute a value in v. And because it's a Taylor series, it's going to be linear in the dx argument, but it can be, and it typically is, nonlinear in the x argument. All right. So, so that's the first thing for type checking, right? If we have a function from u to v, right, then its differential is going to be a function that takes u cross u to v, because it'll take x and it'll also take a new argument, dx, representing the change in x. Now, to muddy the waters a little bit, a lot of times we and other people, textbooks, will write f of x to emphasize that f depends on x. And so that's a little bit of an abusive notation, because we're abusing notation because f is a variable and it's also the name of a function, right? So the variable is the output of the function and we're giving it the same name as the function itself, right? We have a function from u to v and the variable in v. And so we're going to make use of that abuse of notation just because it's convenient and everybody else does it, so why not us? All right, same thing. We can write df of x and dx to emphasize that df depends on both x and dx. And again, that's an abusive notation because we're using df to mean both the function and the output of that function. All right, so when you're type checking, it makes sense to be sure which one of those conventions you're using at any given time. All right, and one last place that's easy to get confused when you're doing type checking. If you look at an expression df of x, right? So that means parentheses like this. It's the differential of the function of the expression f of x. On the other hand, you can also see df of x semicolon dx, right? And there the parentheses go a different way. df is the differential of f, and it has two arguments, x and dx, right? And so both of these notations are used. And this one is easy to tell which is happening because one of them has a dx argument and the other one doesn't. So that's just some warnings about things that are easy to be confused about. Maybe it makes sense to ignore these warnings until you happen to run into one of those confusions, and then go back and see what it means and how to avoid having that confusion. When we're type checking again, it gets a little bit more complicated, but it's the same idea when we have two or more variables. So if we have f is some function of x and y, then df is going to be a function of x, y, dx, and dy, right? And this here is shorter notation for the Taylor series that says the change in f is equal to a function of the change in x and the change in y. And note that again that it's linear in dx and dy and nonlinear in x and y. So I think maybe this is a good place to stop. Yeah, I think this is a good place to stop. So we'll pick back up with differentials next class. Again, don't forget to turn in the quiz for today by half an hour from now, by 41 minutes from now. And my office hours start now, and we'll see you next time. Talk to you later.